This picture is intended to give you a sense of an important feature of a field, that it fills space. It assigns to each point in that space a number or a set of numbers. This picture shows you fog filling space around the trees and in the field. Would be a scalar field because you could represent it by one number for each point in space, the density of the water vapor at that point in space. The electric field and the gravitational field are vector fields because they are fields that exert forces. So here's just a little pictorial way to think about how you might know when such a field is present. You have a probing particle. So let's say three little masses at the ends of strings, and the strings are pinned to a board. The board is lying flat on the table, so there's no force on these little masses. The strings are slack. But now you tilt the board so that gravity exerts a force on the masses. And we see that the little masses draw their strings taut, and the little masses all point down. It shows I'm not holding the board quite square to the surface of the earth. So these little masses serve as probes, as test particles for showing you that there is a field present. Since it's masses that are being acted on, we say there is some kind of a field that exerts a force on a mass, and we call that field a gravitational field. And you can see that we can measure that field, give it a magnitude and a direction, by looking at the ratio of the force exerted to the mass of the test particle. You want the test particle to be small because masses are the sources of fields as well as the objects on which fields act. Masses as sources of fields will affect other masses that are producing the field you're trying to measure. If a test mass were too large, its gravitational field would perturb or disturb the masses that are producing the gravitational field you're trying to measure. The result of using a test particle of too large a mass would be to distort the thing you're trying to measure. So it's important that the mass be small compared to the field strength that you're trying to determine. Now we can make a similar argument with electric charges. If we put electric charges on the little balls, we might observe that the forces on the little balls are quite different than they were when there was no charge. Here I've shown them strings is now drawn tautly towards the left. There's an electric field pulling these things to the left and slightly down. The gravitational field is still there, but usually the electric field overwhelms the gravitational field. The effect is much greater, and so we usually can neglect the presence of the gravitational field when we're worried about what the effect on little particles might be. Now, here again, we define the field in terms of a ratio. So in this case, for the electric field, it is the ratio of the force to the charge on which that force acts. So we're using the charge as a probe to explore the presence of the electric field. Now we can use this force as a probe to map out the field by looking at the acceleration of the unconstrained particles. So here we are accelerating this little particle there. We might accelerate the little particle over here, and we can now assign an acceleration vector to each of these points in space. That acceleration vector is proportional to the electric field at that point in space. We can repeat this procedure different points in space, and you see that the acceleration vectors mark out a smooth curve. You can map these smooth curves from a number of different points, connecting the acceleration vectors together. You get a pattern of lines. These are the field lines. A collection of field lines provides a pictorial representation of the electric field that is useful for thinking about the field. Field lines have the following properties. They start on positive charges. They end on negative charges. Charged particle placed in an electric field accelerates tangentially to the field line. Regions of greater density field lines mean the electric field is stronger there. Here's an example of a simple electric field produced by two sheets of charge of opposite sign close together. The constancy of the field is shown here in the fact that these field lines are evenly spaced. The field lines are not the same thing as the electric field. That point is made by writing an equation for a possible constant electric field here. This vector is assigned to every point in the volume enclosed by the two plates. That field is constant unless you're near the edges, and when you're near the edges, as you see here, the diagram shows the field ceases to be constant. Another important field is the field of the electric dipole, a pair of charges of equal magnitude and opposite sign. The most basic field of all is that of a point charge or a spherically symmetric ball of charge. It's important because all other charge distributions and their electric fields can be built up from them. To remind you again, the field lines are not the same thing as the field. The equation for the electric field of this charge distribution is given here. It specifies the electric field at every point x, y, and z in the space surrounding this ball of charge. You can see that the coordinate system has been set up to have its origin at the center of the charge. Field lines are a two-dimensional representation of the electric field. But of course the electric field, and really the field lines also, are three-dimensional structures. So when we use the word representation, we have to keep in mind that the representation is incomplete and can even be misleading. Let me show you what I mean. Look at the distribution of field lines coming from a spherically symmetric charge. You can look at them in three dimensions. This view that I started with here looks very similar to the radial view that we were looking at before, but that's an artifact of the particular angle at which we're viewing them, because if we rotate our point of view, you'll see they become much more complicated. You can see why this is so if we zoom in, and you'll see that what we have in the center here is an icosahedron, which has the kind of spherical symmetry we want, and we have a field line coming from each of the 20 faces of the icosahedron. And you can see now that the apparent simplicity that we started with was an artifact of the fact that these lines were sitting one on top of the other and hiding their real three-dimensional nature. The consequences of the three-dimensional nature are more apparent here when we look at these field lines from a dipole. You see over here at the right the same 2D pattern that we observed before, but here on the left is what it looks like in perspective in three dimension, and we can rotate this and show that these lines are indeed a three-dimensional structure. Part of what we're looking at is simplified because we're not showing but a limited number of lines. That is, these empty spaces here have actually got lines in them. The structure is interesting to look at from different points of view. If we look at it straight on, it looks a lot like the example of the inset. If we look at it kind of down the barrel of the gun, that is right down the axis of symmetry, it looks like the radial pattern that we were using for a single charge. And this, of course, is clearly an artifact of our angle of view. We need to keep in mind that the electric field extends through all space, that it assigns a vector to every point in space, and that the electric field is a three-dimensional structure, and the electric field lines that we use sometimes to represent the electric field are also a three-dimensional structure.